Welcome students. In the last class, we were discussing in the P block elements about the dinitrogens. Moving further there, let's discuss about the next important element for the nitrogen, that is ammonia. Ammonia. Ammonia, that is NH3. Okay. So the preparation of ammonia can be done in laboratory. In laboratory, they can be prepared by the method. They can be prepared by the NH4Cl NaOH, that is ammonium chloride plus sodium hydroxide. There we will prepare ammonia plus H2O plus NaCl. Okay, NaCl will be prepared out here. NaCl. This is the method for the preparation of ammonia in the laboratory. Also, one more method we can use there, that is ammonium sulfate. Ammonium sulfate can be used and it can be treated with sodium hydroxide to produce ammonia plus water plus sodium sulfate. Okay, so here, due to displacement reaction between the ammonia ion and sodium, we can make ammonia here. Okay, let's move further and see the industrial process for preparation of ammonia. Industrial method for preparation of ammonia, that is termed as Haber's process. Okay, it is been termed as Haber's process. So the Haber's process, in the Haber process, we will see that the hydrogen and nitrogen gas is supplied to a compressor. Okay, the hydrogen and nitrogen gas is supplied to a compression chamber. Chamber where 20 megapascal of pressure is produced out. From this particular chamber, okay, we will transfer the hydrogen and nitrogen gas which is being supplied out here. Okay, hydrogen and nitrogen gas which has been supplied out here and which has been given to compressor chamber. Okay, from there what we will do, we will take this particular gases, this compressed gases, to the catalytic chamber. Okay, we will pass this to the catalytic chamber. This is our catalytic chamber where iron oxide is present with Al2O3 plus K2. Okay. From here, the reaction of the reaction of nitrogen gas with hydrogen will take place. Okay, and formation of what? Formation of ammonia will start out here. Okay, formation of ammonia will start out here. Now from here, using pipes, what we will do? We will collect ammonia. We will connect this ammonia. We will connect this ammonia in a vessel. Okay, in the liquid form. In the liquid form, we will collect it. And the reaction which is been taken place here, it is a reversible reaction. Okay, It is a reversible reaction. So due to it, what will happen? The production of nitrogen and hydrogen will also done in the condensing pipe. Okay, in the chamber where we are storing the ammonia, liquid ammonia. There also what will happen? There also we will see that nitrogen and hydrogen gas is regularly producing out. So we are supplying this nitrogen and hydrogen again back to the place where the compressor chamber was connecting to the uh, input of the nitrogen and hydrogen gas. Okay, so in this way the nitrogen and hydrogen gas will be again available to the process. Okay, so this is the Haber's process. This is the Haber's process for the preparation of ammonia, and this is generally used in industries for preparation of ammonia. So what is the reaction here? The chemical reaction which is taken place here, it is N2 gas plus 3H2 gas gives 2NH3, and here the heat of formation is minus 92.2 kilojoule per mole. Now, if the heat of formation is negative here, it means here that we have to keep the whole process at very low temperature. Okay, we have to keep this process at very low temperature. If you are increasing the pressure, if you are increasing the temperature here, then what will happen? The whole reaction will turn back towards the reverse side. Okay, so we don't want to turn back the reaction towards the reverse side. Therefore, what we will do? We will keep the temperature of the whole reaction very low. Also high pressure will be maintained out here. Okay, high pressure will be maintained out here in order to keep the reaction in the forward direction only. Okay, in order to keep the reaction in the forward direction, we will use some of the catalyst here in order to increase the rate of reaction, to increase the amount of ammonia which is being produced out here. The structure of ammonia, let's talk about the structure of ammonia. So ammonia is a pyramidal, okay, is a pyramidal structured element, sorry, compound. Okay, it is a pyramidal structured compound. The structure for the ammonia will be something like this: three hydrogens covalently bonded to nitrogen, and a lone pair of nitrogen is present here. So the bond length here is 107.1 picometer, and the bond angle here is 107.8 degree. The angle is large here as comparison to that of the other hydrides of group 15 elements, because due to smaller size of nitrogen, what will happen here? The hydrogens here will be present very near to each other. Okay, they will be bonded very near to each other, and due to this reason, the bond pairs of the hydrogens with the nitrogen, it will start to repel each other. Okay, it will start to repel each other, and the angle between the hydrogen bonds and the nitrogen bonds here, it will start to increase, and the final state it will attain is the angle of 107.8 degrees. What are some of the chemical properties of for the ammonia? Chemical properties for ammonia. So first, they are having basic nature. Okay, they are alkaline, they are having alkaline nature or basic nature. Due to presence of due to they can remove they can ammonia gas is highly soluble in water, and in aqueous state they turn red litmus to blue. Okay, it means that they are showing weak basic character there. Okay, they are showing weak basic character there, as they are releasing OH minus ion in the water solution, aqueous solution. Okay, second, NH3 plus H2O gives NH4 plus OH minus. Next, basic nature. Basic nature here you will see that after that there is they act as a Lewis base. They act as a Lewis base. Okay, due to presence of due to presence of lone pair on nitrogen, the formation of coordinate bond takes place, and hence the Lewis base nature is represented. Nature is represented for ammonia. So how we can test this? We can test this by the reaction BF3 plus NH3. Here what we will see? Here we will see that the ammonia will donate its lone pair electron to the electron deficient boron here. Okay, to the electron deficient boron, the nitrogen will donate its lone pair of electron to form complex like structure here. Okay, similarly with ions, silver ions, the ammonia can form complex compounds. Okay, they can form complex compounds, that is AgNH3 twice, AgNH3 twice plus. These are the complex compounds which can be formed by ammonia. Next, action with halogen. So as we have studied previously also in the properties of dinitrogen also, and in the properties of group 15 elements also, nitrogen can form bond with fluorines. Okay, they can form bond with fluorides, but they cannot form stable bonds with the chlorine, bromine and iodine. They will be very highly reactive compounds will be formed out with that of the chlorine, bromine and iodine there. Okay, next is the oxidation of ammonia. For action with hydrogen, let's discuss some of the properties of ammonia with hydrogens for halogens. When ammonia reacts with Cl2, then ammonium chloride will be formed with dinitrogen. Similarly, when ammonia reacts with Br2, ammonium bromide will be formed out here with dinitrogen. Okay, so these are some of the properties of ammonia with the halogens. Next, moving further, and let's see the oxidation of ammonia. What happens when we are undergoing the oxidation for ammonia? So when ammonia has been treated with the copper oxide, they produce copper plus N2 plus 3H2. Okay, dinitrogen will be produced out here. Similarly, if we are reacting the ammonia with a bleaching powder, that is calcium oxychloride here. If we are reacting the if we are reacting the ammonia with the calcium oxychloride here, then what will happen? Here we will see that 2 nitrogen plus CaCl2, okay, 2 dinitrogen, 2 molecules, and CaCl2, Cl2 plus 6H2O will be formed. Similarly, we can directly oxidize ammonia by taking the catalyst, that is platinum here, and heating it at 100,075 degree in the presence of air there. So here what will happen? 4 nitric oxide will be found out and 6 H2O will be found out. Okay. So this is the reaction and this is the Oswald's process reaction. Oswald's process reaction. This particular reaction is nothing other than that of the Oswald's process reaction. Next, moving further, we will see the next topic, that is the combustion of ammonia. So when ammonia has been combustion of ammonia. So when ammonia is being combusted, then dinitrogen and water will be produced out. Okay, dinitrogen and water will be produced out. Formation of amides. How we can form amides with ammonia? So when sodium is reacted with ammonia, when active metals of the group 1 or group 2 elements are being reacted with ammonia and heated, they produces NaNH3, NaNH. Okay, sorry, they will produce NaNH2 plus H2 gas will be released out here. Similarly, 2K plus 2NH3 at 575 Kelvin gives 2KNH2 plus H2. Okay. Uses of ammonia for manufacturing nitric acid, we use ammonia, okay, as a raw material, and sodium carbonate also is produced. We use ammonia as a raw material. Okay. Next, liquid ammonia is used as refrigerant. Liquid ammonia is used as refrigerant. Used for manufacturing of rayon. Manufacturing of rayon. We use ammonia in the manufacturing of rayon. Commonly used for preparation of nitrogenous fertilizers such as urea. Okay, like this, some of the important compounds are also formed by ammonia. Okay, next, the oxides of nitrogen. We will discuss oxides of nitrogen. So the nitrogen is the only element in the group 15 which produces the largest number of oxidation. Okay, the varied number of oxides. Okay, first is the nitrous oxide. First is the nitrous oxide. That is NO. N2O. Sorry, N2O. So nitrous oxide, it is prepared by the method NH4 and NO3. NH4NO3, it has been heated. So here thermal decomposition for sodium nitrate will be taken place and we will produce N2O plus 2H2O. Okay, it is a colorless unreactive gas with faint pleasant smell. Okay, with a faint very faint pleasant smell will be there. Okay, very low pleasant smell will be there. Okay, for the nitrous oxide. It is also termed as laughter gas. Okay, it is also termed as laughter gas because due to its some of the hysteriotic nature. Okay, N2O plus NaNH2 gives NaN3 plus NH3 plus NaOH. Okay, plus NaOH will it will mm, give soda azide here. Okay, it will give soda azides, that is NaN3. In small amount, if it acts as an anesthetic also for minor operations. Okay, in very small amount it acts as anesthetic also for minor operations. Next oxide that is formed with nitrogen is nitric oxide. So the nitric oxide can be prepared by using ammonia. Okay, it can be prepared by using ammonia. When ammonia has been oxidized at 1100 Kelvin and in the presence of platinum catalyst, then 4NO plus O2 is produced. Okay, 4NO plus 6H2O is produced. 6H2O. This has been produced out. But here the NO which has been produced out, it is highly reactive. Okay, it is highly reactive, and this NO will further react with the more oxygen is present out there. But this particular NO, nitric acid, can be also prepared by using this nitric acid can also be prepared by using copper. Okay, copper as the catalyst there. Okay, 3 copper plus 8 HNO. If a copper tube is been treated with the nitric acid, there also CuNO3 twice will be produced out, plus nitric oxide plus H2O will be produced out. Okay, H2O will be produced out. It is a neutral oxide. This is one of the neutral oxide for your hydrogen. For nitrogen. It is a colorless gas. Okay, it is a colorless gas. It is paramagnetic in nature. However, it is liquid and also found in liquid and solid state also. It forms a loose dimer in such a way that the magnetic effect of the two unpaired electrons get cancelled out, and hence it behaves like a paramagnetic material. So this is the dimer structure for nitric acid. Okay, this is the dimer structure for nitric acid. Here it forms a rectangular structure which has 280 238 picometer and 114 picometer length and breadth. Next is the dinitrogen trioxide. Dinitrogen trioxide, that is N2O3. The next oxides for nitrogen, that is N2O3. Okay, so here the nitric oxide which is formed, if when it is reacting with nitric oxide, it is reacting with nitrogen dioxide to form dinitrogen trioxide. Okay, it is blue in color. Okay, it is blue in color, and the preparation here is confirmed by the blue color of the compound which has been formed out there. Next is the nitrogen dioxide. Nitrogen dioxide, that is N2O. So 2 PbNO3 twice gives 2 PbO plus 4 N2O plus O2. Okay, from N2O4 in equilibrium state, it is present in N2O4 form only. Okay, it is present in N2O4 form only. So this is colorless, but when the NO2 is found out, it is brown in color. Okay, it is having a brown colored tint there. Okay. Next is the dinitrogen pentoxide. Dinitrogen pentoxide, N2O4. So dinitrogen pentoxide is being prepared by nitric acid when it is treated with diphosphorus pentoxide to form dinitrogen pentoxide plus metaphosphoric acid. Okay, metaphosphoric acid is being formed out here. N2O5 also exists in colorless solid below 273 Kelvin. Okay, it exists in the form of colorless solid below 273 Kelvin. As the temperature rises, we will see that the color changes to yellow due to the partial decomposition of a colorless N2O5 to brown NO2. Okay, what will happen when we are increasing the temperature here above 273 Kelvin due to changing of N2O5 to NO2? Here the color will change from colorless to yellowish color. Okay, so these were for some of the important oxides for the nitrogen. In the next class we will discuss about the nitric acid, and also we will start the discussion for the compounds of the phosphorus. Okay, so for today's class we are ending the class here only. In the next class we will continue the further part of the chapter. Thank you for watching this video.